Hi, so this is going to be a video over section 4.5 for college algebra out of the Blitzer textbook. So it's titled Exponential Growth and Decay, Modeling Data. So I didn't include the motivational example in this section, but if you'd like, I just made a note here that if you go to page 519 in the textbook, so if you go to here, this is a good read. It gives you a motivational example of exponential growth or decay. Let's see, the Earth's population is an example of exponential growth, right? So you can read over that and learn more about that to maybe get a little glimpse to why it might be important to study exponential growth and where we might be able to use that. All right. So, oops. Let me grab a pen. All right. So then I start here by giving just a definition of exponential. Well, that's weird. Sorry about that. I don't know why that happened. All right, so we're looking at an example of exponential growth, looking at the definition of exponential growth and decay, right? So we have here that we could have a mathematical model for exponential growth or decay is given by one of the following forms, right? So let me just go ahead and make this a little bigger. There we go. All right, so so we can have this as f of t equals a sub 0 e to the kt, or we could write this essentially without the functional notation. So instead of f of t, putting in capital A instead. So then we're told here some information about this equation. So if k happens to be bigger than 0, so if k is positive, then the function is going to model the amount of size of a growing entity, right? So in other words, we're going to have a growth function, right? So if k is positive, right, bigger than 0, we're going to have growth, right? That's what that is saying. So then a sub 0, that's going to be our original amount, right? Or size of the growing entity at time t equals 0, right? So we're going to start out with some value, and that is the initial value, right? A sub 0. Where a is going to be the amount at some time t, and k is the growth rate, right? So it's a constant representing the growth rate, right? And we're going to look at some examples of this, of course. And then the opposites of true is true. If the opposite of k happens, right? So in other words, if k is positive, we looked over up here, then let's consider if, what if k is negative, if k is less than 0. So as you could guess, we're going to have decay, right? So the only value of k that we didn't consider is if k equals 0. So you might wonder, why did we not include that? Well, what happens if k is 0, right? So if k equals 0, right, what we would have is a equals a naught e to the 0 times t, which is the same thing as a sub 0 times e to the 0, which is the same thing as a sub naught times 1, which is the same thing as a sub naught. So in other words, this is showing that nothing is changing, right? So that's why we don't look at if k is equal to 0, because that would just mean that we don't have an increase or a decrease. It's just a constant function. So that would, the graph of that would be a flat line, right? So if this is the initial value, we would just have a flat horizontal line. So this would be the function y equals a sub 0, which would be just some constant number, right? So so that's not an exponential growth or decay, right? So here, you can read that if k is less than 0, then the function models the amount or size of a decaying entity, right? So that, as I was saying, if k is less than 0, we have decay, and then a sub 0 is still the original amount, right? T is the amount of time, and a is the the amount that we have at time t. And then, of course, the difference here is now if k is negative, that k is going to be some decay amount, right? So you can see the functions graphed here on the left and the right. So the one on the left, of course, is exponential growth, right? So you can see as t gets bigger, y is getting bigger, right? And for the b, for this part b, as t gets larger, y is actually going down, right? So we, of course, have decay, right? You can also notice that each graph, the y-intercept is a sub naught, and that's the starting value, right? Which makes sense because that's the value when t equals 0, right? And t is my x-axis, so that would be a y-intercept, right? So if you look at that for a moment, you might be thinking like, wow, I don't know, it seems pretty familiar from the beginning of the chapter, and that's and if you're thinking that's because this form is very familiar. We just looked at it in a very specific format, right? So we're looking at it more general, right? So before we looked at for an interest rate, right? We looked at A equals P ERT. Right, so this was continuous compounding, right, formula, where P is principal, right, R was the interest rate, and A was the amount at time t still, right? So you can see here how the variables match up, right? This is the same thing if I want to write it in this form, e to the kt, right? These are going to match up, where the principal, right, in an account is like your starting amount, right? So that's why we can think of those as being equivalent, P and A sub naught. And then R was my interest rate, and K is my, growth or decay rate. So that makes sense, right? Because that's the rate that my money is growing by, right? And of course, T matches up, right? That's just the time that's going by. And the A's, of course, match up, right? Because that's just the amount in the account, right? So you can see how related those are, right? So we're looking at exponential growth and decay in this form, right? So just as a refresher, we already looked at a form of this. Now we're just talking about this in more general, right, context. Whoops. So now this page is over top. All right, so now what I want to take a look at is an example of using this form. So you can see here, so the title of this example is Modeling the Growth of a U.S. Population. So we have the graph in figure 4.22 shows the U.S. population in millions for 5 selected years from 1970 through 2010. So in 1970, the U.S. population was 203.3 million. By 2010, it had grown to 308.7 million. So we want to find an exponential growth function that models the data for 1970 through 2010. So let's do that, right? So for part A, we're trying to find this exponential growth function, right? So what we have is A equals A sub 0 e to the kt, right? So it's common here, right? For dealing with time, right? If you read over this and think through this for a moment, our initial amount is basically 1970, right? So this is information about my initial amount, right? So in other words, at or maybe we should say n, right? So in the year 1970, we have 203 0.3 million people, right? And then time happened. So now in 2010, we have 308.7 million people, right? So you can see that we had growth in between, 203 to 308 million people, right? We added, roughly 105 or so million people over that time period. So we know we're going to have growth, right? So maybe just a note to yourself is I know that K is going to be positive, right? So I know this because we have growth. And then another way to think about it is, again, this is information about A sub naught, right? So if I want the 203 million to be A sub naught, then I'm going to want 1970, the T value, to be 0 for that, right? So of course, what we can do then to make that happen is let's let T equal the number of years after 1970, right? So in doing so, right, that would satisfy the condition we're kind of looking for, right? If this is my initial value, I want T to be 0 at the year 1970, so that makes that happen, right? So that means A sub naught is going to be the 203.3 million. Right? So then also what I know, right? So this point here, we're going to have T equals 2010 minus 1970, right, to calculate the number of years past 1970. That would give me, 40, right? So when T is 40, I know that A is 308.7 million. Right? So this was information for the year 2010. Right? So if I plug what we know into the equation, what's missing is the K value, right? All I know is that K is positive at this point because we have growth, but I don't know what K is. So in order to find K, right, we just need to plug in what we know and solve for that, right? It's kind of like, when you're doing a linear equation and you don't know the intercept, right? You can plug in the slope and a point and you can solve for the missing variable that we don't know, right? So basically, in order to have an equation, right, let me maybe use a different color, maybe blue, right? In order to have an equation, what I need to be able to fill in a number here, and I need to be able to fill in a number for K, right? Those are my two constants, right? Kind of like when you have a linear function, right? You have y equals mx plus b, right? This b value is like my starting value. That's similar to A sub naught, right? That's kind of like b. And m is my rate of change. That's kind of like k, right? So we kind of have some similarities, between a linear function and an exponential function. So those are the similarities. So I need to find those. I need a value for both of those. But I already know A sub naught, right? So I already have one of the missing pieces of the puzzle, right, if you will. So now I need to find the other one. So if we plug those values in, right? So for A, I'm going to have 308.7. And then A sub naught is 203.3. Right? And then I'm going to have E raised to the TK. So T was 40, right? So this would be 40 times K. Right? So this is what we know. We need to solve for K. Solve for K. Right? So in order to solve for k, since I have an exponent in the in the denominator, or excuse me, in the since I have a variable in the exponent, sorry, I need to be able to solve for k. I'm going to have to end up taking the logarithm of both sides, right? So if you notice, I basically have a number times e to the some power, and then equals some number over here, right? It'd be really nice if I could get it in this form. Some, like, a number equals e to the 40k, right? So I can do that by dividing by 203.3 to both sides, right? So if I divide both sides by 203.3, what I'll end up getting is 308.7 divided by 203.3. And I'm not going to plug that in my calculator and try to get a decimal approximation. I want to keep this as exact as possible until the end, right? You don't want to use a rounded answer just to get another answer that you're going to round. So I'm just going to leave it in that form. And that's going to be equal to e to the 40k, right? And then as I was saying before, now what we can do is take the log of both sides, right? So I'm actually going to use the natural log, right? So I can take the natural log of both sides and still have both sides be equivalent to each other, right? So I'm able to do that. So now I can use properties of logs. So the natural log of e to the 40k is just going to be left with what's the exponent of e, right? This is just going to be 40k left here, right? So if you don't forget that inverse rule, right? You can also use the property that when I have a natural log of something raised to a power, I can pull that power as a product in front. So that would give me 40 times k times the natural log of e, right? And the natural log of e, of course, is just 1. So that's just 40k times 1, which is, of course, just 40k, right? So you could, this is kind of like my side work. You could work it out like that as well if you didn't remember how to go from here to here, right? So then on the left-hand side, I would still have the natural log of 308.7 over 203.3. Right? And don't forget that when you have the log of some constant, that's just a number, right? So this left-hand side, this is just a number, right? So basically I have a number equals a number times 40, so I have a number equals some number times k. I'm trying to solve for k. We just need to divide both sides by 40, right, to get k by itself. So k is equal to the natural log of 308.7 divided by 203.3, and that's divided by 40, right? So you can plug that in your calculator to find that. So let me just go split screen here. So we can just hit the natural log of 308.7 divided by 203.3, and that's all divided by 40. You can see that we get roughly 0.01, right? So I'll just go out to 2 decimal places. So k is approximately 0.01, right? So that now that I know what k is, right, I can plug in what we know. So remember, the model looks like this, right, in general, right? What we need is this number and this number, because t, right, that's my input. Right, remember e, that's just a number, and this is my output. Right, so that's how my function works. I have an input and I get an output, so I need to know these two things I circled in red, right? And we know what those are now, right? So to be able to have an equation that models this, I would have a equals A sub naught was 203.3. Then we have E raised to the 0.01 t. Right? So this is the answer for part A. Right? There's my model. All right. So now that we have a model, part B, right? So if you look back up, part B was by which year will the U.S. population reach 335 million, right? So let me just go over here to the side. Right. So part B, we want to know when the U.S. population will reach 335 million, right? Essentially, what we're asking for is we want to know what T is, right? When A equals 335, right? That's essentially what's being asked, right? And notice that my initial population is in millions, so I don't, since it's in the same units as what I'm trying to get into, I don't have to worry about that, right? But hopefully you would know that, you know, if this was 330, like let's say you were trying to estimate, well, when will the U.S. population reach, 335 trillion or billion or, a different unit, that work's going to look a little differently, right? So I just want to point out that, since the units are the same, I don't have to worry about that right now. But you want to be careful, though, because it says what year will the U.S. population reach, right? So I want to find what T is when A equals 335, but then I'm going to have to take T and add 1970 to it to get the year, right? And this is what we're after, right, is the year. That's what we really want, right? So maybe just some notes to myself of what we're doing and whatnot. Another thing to note is just we already have our model, which is 203.3 e raised to the 0.01 to the t power, right? So basically, what I want to do is plug in 335 for A and solve for t, right? So this would give me 335 equals 203.3 raised to e raised to 0.01 times t. So then first what I would want to do is divide both sides by 203.3, right? So that way it gets in that nice form of a number equals e to some power, right? So then by doing that, I get 335 divided by 203.3 equals e to 0.01 times t, right? And then what I can do is take the natural log of both sides, right? And just like we discussed before, right? On the right-hand side, we're going to have, one of those nice properties of logs, right? That's just going to leave us with the exponent, because I'm taking the log of base e and then the same base e raised to an exponent. So we're left with just an exponent. That's one of the cancellation properties we looked at before. So then on the left, I would just have the same thing, which is this is going to be just a number, right? So then now, of course, to solve for t, I'm going to divide both sides by 0.01, right? So t is going to equal the natural log of 335 over 203.3, all divided by 0.01, right? And don't forget that this guy, this is just some number, right? So we're just solving for a variable like we've done before. Right, so I can solve for this really quickly. We would take, so natural log of 335 divided by 203.3. And then we divide that by 0.01. And we're getting 49.94, right, roughly. So T is approximately, 50, right? Pretty darn close. So then, again, if don't forget that we were asked for, at what year, right? So to find the year, we would take 50 plus 1970, which is 2020, right? So in the year 2020, the U.S. population will reach 335 million, right, according to our model, right? All right, so another type of example that we want to look at is called half-life, right? So half-life, I have a statement here. The half-life of a substance is the time required for half of a given sample to disintegrate, right? So if we know a certain time, every time that amount of time goes by, the item that we have will be half as much, right? So, let's say the half-life is 10 years, right? After 10 years, you're going to have 50% of your item left. And then after another 10 years, you would have half of 50%, which would be 25%, right? And then if another year, another 10 years goes by, you'd be down to, half of 25%, which would be 12.5%, right? And so forth. So it keeps cutting in half as that cycle, that half-life keeps occurring, right? So in our example, we have, so it says, use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14, right? So in other words, in looking at part A, right, so just to make this clear, at, initially, you're going to have 100% of your carbon-14, right? So we'll call this T. So at time 0, you're going to have 100%. And then as we increase by 5,715 years, right? So as T equals 5,715, now you're going to have 50% of your carbon-14 item, right? And it doesn't matter how much you start with. You just have half left, right? That's the definition of half-life. So then, if another 5,715 years goes by, right? So 5,715 times 2, right? So if time was 11,430, right? So in other words, we added another 5,715 years. This would now be at 25%, right? So notice over here, we keep multiplying by 0.5, right? And over here, we keep increasing by the half-life, 5,715, right? Oops, that's not very clear. Right. So that illustration, really isn't part of the answer, just to help us, get to thinking about what the half-life is if you haven't seen that before, right? So with part A, though, right, we know that we have exponential decay, right? So what do I know? I know I'm going to have a function that looks like this, right? A equals a sub 0 e to the kt, right? And in this case, since I have decay, I know that k is going to be less than 0, right? Since we have decay, right, we're told that in the problem, right? We have decay, and of course this would be decay, right? It keeps cutting in half, right? So it's going down, right? And then also another fact that we know is that A is going to equal your initial amount divided by 2 at the time 5,715. Right? This is another fact we know, right? Just by half-life, right? So I'm saying when this many years goes by, the amount we have at time t, which is a, right? That's what the a value represents. You're going to take whatever you had, divide by 2, right? That's 50%, right? Half of what you had. So if we plug these things into what we know into the equation, then we can begin to solve for k, right? That's what we need, right? So we need to know an initial amount, and we need to know k in order to have a model. But something we're going to find is that with half-life, we actually don't need to know the original amount in order to solve, in order to come up with a model, right? So let me show you why that happens, right? So in for A, I can plug in a sub 0 divided by 2, right? So I'm just plugging in this value for A into the equation, and then we'd have a sub 0 e to the 5,715 times k, right? We want to solve for k. So one thing you'll notice is, the next thing I'd want to do is get rid of this a naught, right? So if I divide both sides by a naught, right, what's going to happen is on the left here, this is going to become 1/2, right? Because a sub naught divided by 2 times 1 over a sub naught, right? These are going to cancel each other out, and we're left with 1/2, right? So we have 1/2 equals e to the 5,715k, right? So now we can keep solving for k. So, we've done this a couple of times now. We just need to take the natural log of both sides, right? So then this becomes a natural log of 0.5, right? I just take 1/2 and put it as 0.5, right? Those are exactly equal to each other. And then this would be equal to, so we're going to be left with just the exponent, 5,715 times k. So then now to solve for k, I would divide both sides by 5,715. And we get k equals the natural log of 1/2 divided by 5,715. We can plug that in our calculator to come up with an approximation, right? So we would take the natural log of 0.5 divided by 5,715, and we get this amount, right? And notice that this is an exponential notation, right? So let me just make this clear. Let me maybe get a different color, right? So my answer I got was negative 1.21. I'll just do, let's see, 211. I'll just do 3 decimal. Yeah, I'll just do the 3 decimals. So we got 1.21. Nope, I'm sorry. That wouldn't be there. I had too many ones there. Sorry, that's what was tripping me up. So we got 1.21. I'll just write that out, and then we have e to the negative 4, right? So I just copied down my answer, but I only went out to 2 decimal spots, right? So what this means, right? This means negative 1.21 times 10 to the minus 4, right? This is a way your calculator shows scientific notation, right? So all this is going to do, right, if you should already know scientific notation, right? So what this negative 4 does is going to move the decimal spot 4 spots to the left, right? Let me see if I can move over a little bit. Right? So there's 1, 2, 3, 4. So we put zeros in these placeholders, right? So we end up getting negative 0 point, and then what, 3 zeros, right? 1, 2, 3, 1, 2, 1. Right? So this is approximately equal to k. Right? That value. So that's what we would get for this value, right, for k. So then my function, right, my model, my decay model, would be a equals a sub 0 e to the negative 0.0000121 times t. Right? So that function, right, how it's written, that's going to model decay for a carbon-14 model, right? So then, to work through a problem, we need to be able to plug in an initial amount and the time that's occurring, and then we can find the output, the amount left at time t, right? So that's the solution for part A. So then I'm going to come off to the side to work part B, so I don't have any room left. Right? So then part B, let's see, we were told that in 1947, we have some earthenware jars containing what are known as the Dead Sea Scrolls were found by an Arab, Podonian herdsman. Analysis indicated that the scroll wrapping contained 76% of the original carbon-14. Estimate the age of the Dead Sea Scrolls, right? So this is a very common example for half-life, and that's something that scientists do to estimate the age of something. So that's called carbon dating. So we know like how fast carbon degenerates. So if we can estimate how much was there, you can get a percentage and be able to estimate how much time occurred or went by, right? So that's all this example is doing. So we can use our model that we found from part A. So we have A equals A sub naught E raised to the negative 0.00. Let's see, there were three zeros and then 1, 2, 1 to the t, right? All right, so then the key part here is that it says there's 76% of the original carbon left, right? So in other words, if I take the amount I have now and divide it by what we started with, right, we get 0.76, right, which is 76%, right? So hopefully that makes sense, right? If I take the amount I have now and divide by what I started with, then we're getting this percentage, right? So by knowing that fact, I want to be able to plug this in somewhere, right? So I don't know exactly how much we started with, but I know the percentage of what's left, right? This A divided by A naught. So what I can do is if I divide both sides by A naught, I will have the equation in this form. right? So then now I can just take this value, 0.76, and plug it in, substitute it in now, right? So then I would have 0.76 equals e to the negative 0.0000121 times t, right? And then, of course, our technique to be able to solve for the exponent in the denominator, or I don't know why I keep saying denominator, in the exponent, right? We're trying to solve for this variable in the exponent. We can just take the natural log of both sides. So we get the natural log of 0.76 equals the exponent. Right? So then to solve for t, I would divide both sides by this negative coefficient. Right? And we're left with t equals the natural log of 0.76. all divided by negative 0.30121, right? And if you throw that in your calculator, you should get approximately 2,268. Right? So the important thing to understand is that this, right, is the age in 1947, right? So currently we're in 2019, right? So we need to add 72 years to this to find how old it is today, right? So if that doesn't make sense, this is how old the documents were, but in this year, 1947, right? So there are 72 more years that went by to get us to the current year, which is 2019, right? So in order to find the age today, right, we would have to take this number, 2,268, and add 72 to it. Whoops. Sorry about that. I need to scroll down. Right? To get 2,340. Right? So the scrolls are 2,340 years old in the year 2019. Right? So that's the answer we were asking for. Right? The estimated age of the scrolls. All right. So now the next topic we want to look at are something called logistic growth models, right? So I have just a statement here that, from population growth to spread of an epidemic, nothing on Earth can grow exponentially indefinitely, right? Growth is always limited, right? So in other words, we can't just keep growing forever. There's maybe some kind of cap, maybe some horizontal asymptote that limits growth, right? So that's where this logistic model comes in, right? So you can see here the equation for a logistic growth model and a graph of a logistic growth model, and you can see there's a limit, a horizontal asymptote, right? So let's work through a problem. So example 3, we're modeling the spread of flu. So we're given a function that describes the number of people, f of t, who have become ill with the flu after t weeks after its initial outbreak in a town with 30,000 inhabitants. So part A is that we want to find how many people will become ill with the flu, how many people became ill with the flu when the epidemic began, right? So in other words, we want to find f of 0, right? This would be like the initial value, right? So if I plug this in, we would have 30,000 divided by 1 plus 20 e to the negative 1.5 times 0, right? So this exponent for e would, of course, be 0. So we'd have 30,000 over 1 plus 20 e to the 0 power, right? So because negative 1.5 times 0 is, of course, 0. So then e to the 0 is just 1, right? So this ends up becoming 30,000 divided by 1 plus 20, which is 21, right? So this value is approximately 1429. So 1,429, right? So approximately 1,429 people were ill when the epidemic began, right? That's what we were trying to find. So then part B, it says how many people were ill by the end of the 4th week, right? So remember, T is, T weeks, right, that went by. So if we're at the end of the 4th week, then 4 weeks went by. So I essentially want to find f of 4, right? So f of 4 would be 30,000 divided by 1 plus 20 raised to the e raised to the negative 1.5 times 4, right? So if you plug that in your calculator, you should get approximately 28,583. So 28,583 people, were ill at the end of week 4, right? So then part C says, what is the limiting size of f of t, the population that becomes ill, right? So a couple of ways to think about this, right? So, if we just think about it in terms of I have a city with 30,000 people, if we try to calculate how many of those people in that town can become ill, what's the limiting size? Well, the limiting size would just be the population in that town, right? 30,000, right? In other words, if there's only 30,000 people in a town, then there can't be more than that get sick in the town, right? That's the limiting factor here, right? Another way to think about it is if you have this function, f of t equals c over 1 plus a e to the negative bt, it turns out that this function, the graph of this function, is going to have a horizontal asymptote at y equals c. So y equals c is going to be the horizontal asymptote, right? So in other words, c is the limiting size. Right? So you could think about that one either way. Right? So when you have this logistic growth model, you're going to have a horizontal asymptote at y equals c. That whatever number's in the numerator, right, is c. Right? So then the bottom of the page are just some scatter plots for some models. Right? So if we want to model data, right, here's we're looking at 3 different types of models: exponential, logarithmic, or linear. And then also we are we have two examples of each way, right? One where we have like a growth and a decay, right? So you can see the constraints that happen, right? But you want to pay attention to the pictures, like how those scatter plots will look roughly, so then we can maybe estimate what kind of model would be appropriate. So for example, in the next problem we have, we're looking at the growth of the human brain, right? You can see here that we have a table of growth rates. So you have age, percent of adult brain size. or excuse me, the percentage of adult-sized brain. Excuse me. Right, so we're told here that that data is going to indicate that between the ages of 1 and 11, the human brain does not grow linearly or steadily. A scatter plot for the data is shown. What type of function would be a good choice for modeling the data, right? So one thing you want to notice about the shape, right, is that we're increasing quickly, but then we kind of level off. Right, this isn't gonna, ever be 100%, right, or over 100%. It can't be, right? You can't have more than 100% of your adult brains, right? So here is going to be like a horizontal asymptote, right? So if we have something that's increasing rapidly and then kind of leveling off, right? If we go back to the models, right, that's gonna look like this example, right? We're increasing rapidly and then kind of leveling off, where the difference between the logarithmic and the exponential is, notice the exponential is like increasing without bound, right? It's just like it just keeps going up, or here it just keeps decreasing, right? So what we're trying to find is, maybe what type of function would be a good choice for modeling the data. So, since we're increasing rapidly and then it begins to level off, we would say that logarithmic would be a good choice for this example, right? So then I have here another part from the text. So this is page 525. So this is going to define R, which is called the correlation coefficient. So maybe if you've taken statistics before, you may have done linear regression. Or maybe you've done it before. Maybe you've taken like a high school stats class, or maybe looked at that in a previous course. It's not too uncommon. But what a correlation coefficient does is it's a measurement of essentially how well the data points fit on the line, or fit the model, right? What we're trying to do is minimize the distance between the actual points, which are the data points, and the model, right? So here I can show you maybe just a quick picture, right? So like if we have this scatter plot, right, and if we're trying to fit this maybe a linear line, right, then the idea is I want to have the least amount of distance between the data point and the point that would be on the model, right, for that same x value, right? So like if I draw vertical line to the line, right, that's what models that, right? So if I had if I had that scatter plot, maybe something like this, versus a scatter plot that looked like this, right? You could imagine that the one on the right, this is going to have a larger R value than the one on the left, right? Because if it measures that correlation, that strength, when I fit my linear model over here, there's going to be more distance from each point to the line, where this one over here, I try to make pretty much every point be on the line, right? So this R value over here might be like 0.99, or something like that, right? Very strong. And over here, maybe, I don't know, it's like 0.8 or something, right? It's less than, the one on the right's greater than, right? The correlation coefficient is going to be bigger, right? Right? So you can see here that the value of r is always going to be between -1 and 1, right? So a positive r means that x values increase. As x increases, so does y, right? So we have growth. And a negative r means that the x values increase, the y decreases, so we have decay. Then we're told the closer that r is to -1 or 1, the better the model fits the data, right? So in other words, when your numbers are closer to 0, that's bad, right? We want them to be closer to 1 or -1, right? So then this next sentence will make sense after we look at the next example, right? So let's look at that. Oops, hang on, it won't let me scroll down. Try this. All right, there we go. Let me just make this bigger. All right. All right, so we have this example. So it says data for the world population are shown in table 4.10. Using a graphing utilities linear regression feature and exponential regression feature, we enter the data and obtain the model shown in figure 4.28, right? So basically we just enter this data into the calculator, and we can pop out the linear regression or exponential regression functions, and that will actually give us the equation. And it will also give you the R values, right? So let me just real quickly show you of something that you'll have to do on your calculator in order to get the correlation coefficient. Let me just make this bigger, so since we're focusing on the calculator right now. First off, what you're going to have to do is go to second catalog, right? So you hit second, and then above 0 is catalog, and you're going to scroll down until you find diagnostic on. Right, diagnostic on. You're going to hit enter, and you're going to hit enter again, and then it should say done, right? So you only have to do that one time, right? So by default, your calculator doesn't show you the correlation coefficient value, so you have to turn that on, and you only have to do it once. So you don't have to do that every time, right? Just do it once, and then it'll always stay on, right? So then now what we want to do is enter in our data. So to do that, you're going to hit stat, and then edit. And then in L1, I'm going to put my X values. So 1, 11, 21, 31, 41, 51, 61. And then in L2, I enter my Y values in. So 2.6, 3, 3.7, 4.5, 5.3, 6.1, 6.9, right? And we can find those. So now to get those printouts that were shown, you go to stat and then go over to calculate, and then you can see option 4 is a linear regression, and then the other one was exponential. So that's that 0 option, right? So like if I hit that 0 option, then I put X in L1 and Y in L2. That's what's going to be default. Then you can just go down to calculate, and there's the same output shown there in the book, right? So this is reminding you of what the form looks like, and these are the values, right? So in this case, A is my initial value, and then we have this B value, right? That's the base of the exponent, right? And then if you want to find the other one, you'd go to stat, and then 4 and 8 are identical. Just notice the difference is A in this form is slope, where a in this case would be your y-intercept, right? So those are in a different form. Right? So we can find that. Right? So that's how you can use your calculator to find each of those. All right, so for A, what we're asked to do is express each model in functional notation with numbers rounded to 3 decimal places, right? So we can easily do that. Right? So for part A, for the linear regression, we would have f of x equals 0.074, right? Rounding a to 3 decimal places, and then we would have times x plus b rounded to 3 decimal places is 2.294. Right? So then for the exponential regression, we would have, I'll use g of x. G of x would be 2.577 times 1.017 raised to the x power. Right? Where, in this case, f of x and g of x are world population in billions, and x equals the number of years after 1949. Right? So just using the information from the table, right, reminds me of what the units represent, right? What the variables represent in the units. So then part B says, how well do the functions model the world population in 2000, right? So in 2000, we're asking for an x value of 51, right? So for part B, if we take 2000 minus 1949, because we're looking at, because x is the number of years after 1949, this is 51, right? So in other words, x equals 51 for the year 2000. Oops. So I could find f of 51 and g of 51 to come up with those values. So if we plug those into our calculator, f of 51, you should get 6.119, and g of 51, you should get 6.041. Right? So, f of 51, of course, would look like, 0.0774 times 51 plus the 2.294, right? And then g of 51 would, of course, be the 2.577 times 1.017 raised to the 51st power, right? And that's where you can get those values. So if we look at the table in 2000, this is actually what happened. So the actual amount is 6.1, and our models are close to that, right? Both of these numbers are close to 6.1. So both models seem to be doing a good job. So then part C is asking about, so it says by one projection, the world population is expected to reach 8 billion in the year 2026. Which function serves as a better model for this prediction? Right? So in other words, we want to find f of 77 and g of 77 and see, which one seems to be a better fit for the 8, right? So what I'm going to do is plug these in my calculator, right? So let me clear all of this. So what I want to graph is I want to graph a scatter plot. So I'm going to hit plot 1, turn that on. And then y1, I'll put the linear function. So that was 0.074 x plus 2.294. And then in for y2, I'm going to put the exponential regression, which was 2.577 times 1.017 raised to the x power, right? So we get that. And then I'm going to hit second and then get the stat plot, so that way I can work with stat plot. And this is, already by default, it's what I was hoping for. I'm going to have a scatter plot with these lines. The x list is, going to be L1 and the y's are L2. And we can pick what we want the mark to look like and the color. So if I go back to y equals, I'm already using blue and red. So let me go back to stat plot, and I'm going to change the color of these points. So that way, in case they're on the line, I don't want them to be blue or red. So let's do green, right? So I have blue, red, and green showing up on the graph. So if I hit zoom, I'm going to hit, let's try zoom stat, option 9. That should give me a good fit. So here, we can just kind of see a nice diagram between the scatter plot, which is the green lines, and the blue function and the red function, right? And then let's see. And then so what we were doing is trying to find f of 77 and g of 77, right? So we can find that pretty quickly with the calculator. So I think I've shown this to you before. But if you hit vars, the variables button here by clear, and then go over to y variables and then hit function, you can pick what function. So y1 was the linear function, right? So that would be f. So if I wanted to find f of 77, I can just type 77 in parentheses, and that will do functional notation for me, right? So plugging 77 into a linear function, we get this value, 7.992, which is really close to the 8 billion that we were hoping for. And then if I repeat the steps, go to variables and go to y variables and then hit function, we want to go down to y2. All right. So I want to type, I want to plug 77 into y2 as well, which is the exponential regression. I get roughly 9.436866, right? Let me just make sure 2.577, 1.017. Yeah, so I have that, making sure I have that typed in correctly. Yeah, so those are the two outputs that we get. And notice that the linear function f of x is going to be a better job for predicting the 8 billion prediction, right? So in other words, let me go back to here. Right? So we were working on part C. Right? So if you weren't following along, let me just write this down. So for part C, what we are trying to do is plug 77 in, right? Because 2026 minus 1949 is 77. So we're trying to see which model is a good predictor for 8 billion people in the year 2026, right? So we found f of 77 to be this 7.992 number, and g of 77, which is the exponential function, that was 9.364. Right? So this one, the linear function, is going to do a better job for predicting the 8, right? Because the exponential is way over, right? If we hit the graph, maybe we could add y equals, let's say, so we were doing 8 billion, so I'm going to add y equals 8 to the graph. See if it, so it's not showing up. Let me go to the window, and I need to increase the y max. Maybe we'll increase it by 10. Let's see if that shows up nicely. There. So now let's increase the x. I don't know. We'll go 80. Right? So basically, just go full screen right here. Right, so if we're looking at the graph, right, so remember this blue line is a linear regression function. This red line is the exponential regression function. This black line are, collection of all the y points for that 8 billion population. And then and then the green dots are the actual data points from the scatter plot, right? So basically what we found is we found this intersection point here between the black and blue line. That was where the linear function reaches 8, right, at that time, 77. So if we would go straight up, you would hit that g of 77 value, which would be that 9.4 number that we got, right? It was 9.364, right? So just kind of putting it all together in a graph. All right. So then we have one more type of example to practice. So let me let's see. I need to make this. Let me make this larger. Let's see. All right. So now what we want to be able to do is express y equals a times b to the x in base e, right? So if you notice, like the previous exponential regression function was in that form, a times b to the x is what our calculator gave us. So there might be times we want to rewrite it in the e to the some power form, right? The continuous growth rate form. So we can do that pretty easily, right? What you're going to do is notice this b value, it just becomes this e raised to the natural log of b, right? So b, we're going to replace that with e to the natural log of b, right? That's the only difference in this form. Everything else stays the same, right? We're going to have that raised to x and then multiplied by a out front, right? So in this example, we have seen that the function g of x equals 2.577 times 1.017 to the x models the world population, g of x in billions, x after years 1949. Rewrite the model in terms of base e, right? So see, that was the exact function that we got earlier, right, in that last example. So g of x is going to equal 2.577 times e raised to the natural log of 1.017, and that will be times x, right? That's just following that equivalency form, right? Which makes sense, right? Because this natural log part, this part in parentheses, you're asking yourself, that's the exponent for base e that gives you 1.017, right? So this whole value equals 1.017, right? That's why we can just replace it in between, and that natural log is just going to be whatever that exponent is, right? Trying to find it. So if you take the natural log of 1.017, you should get approximately 0.017, right? So you could verify that. So we want to take the natural log of 1.017, and if we round to, say I rounded to 3 decimal places, right, we get roughly that 0.017, right? I just want to point out that you don't just take 1 away from natural log, right? It's just kind of a coincidence that it rounds to that, right? So it's nice to see it in the calculator, so that way you don't think that, right? So then we could rewrite this as g of x equals 2.577. This would be times e to the 0.017 to the x times x, right? So then as extra practice, right, why don't you try rewriting y equals 4 times 7.8 to the x in terms of base e, right? So if you pause the video and try that one on your own, the answer you should get is, y equals 4 times e raised to the natural log of 7.8 times x, which is, we get y equals, so, excuse me, the natural log of 7.8, right, is approximately 2.054. So if I plug that in, I'd have 4 times e to the 2.054 times x, right? So that would be the answer, right? All right, so that's all I have for this section, and we're at almost an hour and 20 minutes, so that's plenty of material to cover for missing class on Thursday. Thanks.